Okay, so let's start with volatiles. Originally, I think in the plan I had said that we were going to talk about granites this week, but I just think with the having talked about subduction zones and all the fluids going on, it's such a nice lead into volatiles and then volcanic eruptions. So we're going to do that first, and then we'll cover granites next week. So we finished just before Christmas talking about subduction zones. We talked about the fact that you have a slab descending, and as it warms up, fluids are driven off. This causes fluid flux melting. And then we get a magmatic arc above that. There's a lot of water. Usually this is giving us these hydrous minerals like amphibole and biotite. And because we have these dense mafic magmas that are trying to erupt through existing crust, and we have these complex plumbing systems where we potentially have big stacks of sills and magma chambers connected by dikes throughout the crust. So we're going to look at what happens to these fluids in magmatic systems once they get a bit close to the surface. So volatile elements are elements that typically form magmatic or volcanic gases. There's also another sort of volatile element that people talk about in terms of formation of the planets and stuff. We're not worried about that. So when we say volcanic gases, these are the things that come out during volcanic eruptions as part of volcanic plumes or degassing from lava flows. But they also have this low temperature degassing from things like fumaroles. This is kind of like degassing between eruptive events. And then of course you guys will be really familiar with vesicles by now. These are little trapped gas bubbles that were there when the magma froze. And sometimes they remain empty, sometimes they get filled in by other crap later. In terms of the volatiles that are most important for what we're interested in here, which is volcanic eruptions and the way that magmas behave, water, carbon dioxide, and some form of sulfur. By the time it degasses and erupts, it's usually sulfur dioxide, but it can be in different states when it's in the magma. Less important, but still important, there's the halogens. These are fluorine and chlorine that usually make hydrochloric or hydrofluoric acid or hydrogen fluoride, hydrogen chloride in magmas. Bromine and iodine are just not that abundant, so they're not as big an issue. And then the noble gases, most of these are going to be helium, neon, and argon. There's also a little bit of krypton, xenon. Radon is only formed by radioactive decay. It's not always present. Okay. So why should we care about these? They're a huge control on the style of volcanic eruptions. They are very, very important for how volcanoes end up. How we get magmas to even erupt as lavas at the surface, and then how they erupt is very much controlled by volatiles. Another important thing, if we're interested in the evolution of the Earth's atmosphere for life, if we're worried about climate change, well, the atmosphere is ultimately sourced from the Earth's mantle, and it's continually cycled through this process called deep volatile cycling. And I've got an image here which shows it for carbon, but similar things apply for other volatile elements. And you can see that basically we have carbon gets brought down into the deep mantle by subduction, and some of it will eventually come back up again through volcanic eruptions.
I have a question for
Go
you.
for it.
What's the slab on the right? Is that,
Yeah, so these are both subducting slabs. One is subducting under a continent, so this would be a continental arc. One's subducting under oceanic crust, so it would be an oceanic arc. We'll get back to this in a bit. So in terms of eruptions, we have major climatic effects from large eruptions. On the shorter timescales, these can be things like sulfate aerosols that can actually cool Earth's temperature after a big eruption. But probably the bigger, longer-term issue is CO2, and we do actually see this correlation that's been pointed out a number of times in the past between large igneous province events and mass extinctions. So most people are probably familiar with the end Cretaceous extinction when the dinosaurs went extinct, and obviously I think the leading theory is that it's the meteorite impact in the Chicxulub crater in Mexico. But there's kind of this idea that maybe the eruption of the Deccan traps soften them up, and certain people have argued for the relative importance of the large igneous province compared to the meteorite. The biggest mass extinction ever at the end Permian coincides with the Siberian traps, which is one of the biggest large igneous provinces on Earth. And so the idea here is that some combination of gases drove climate change, acid rain, darkening of the sky, all this kind of thing that could contribute to mass extinction. And finally, volatile element-rich fluids can mobilize and concentrate metals, which are crucial for mining and obviously all the technology and stuff that we use. The gold mine that we saw on the Spain trip is actually a good example of this, so we'll talk about that a bit later. Volatile elements are usually incompatible during both mantle melting and magma differentiation. So if we think back to our incompatible element, this is a fractional melting diagram. So the most incompatible elements are highest concentrations in the magma at the lowest degrees of melting. And this one over here is for fractional crystallization. And so as the melt is removed and as minerals crystallize from the melt, the volatile elements get increasingly concentrated into the melt. So we have higher volatile contents in small degree melts, evolved melts that have undergone more fractional crystallization and differentiation, and then melts with volatile rich sources. So obviously subduction zones, because we got fluid flux melting, the primary magmas in subduction zones start out with much higher volatile contents. Yeah.
Small degree melts, could you just quickly explain?
That's if when we're partially melting the mantle, we only melt it a little bit.
Okay.
High degree melt would be melt it a lot. Okay, so there's a bit of a difference though compared to other incompatible elements. So volatiles are incompatible in that they don't sit in minerals, but they do like to be in a gas phase. So essentially, if we increase the concentration of volatile elements too much, then volatiles will exsolve, which means that they basically create a gas. And we call this reaching volatile saturation. And this can happen both through fractional crystallization, we just increase the volatile content until we hit volatile saturation, or changes in pressure, temperature, or magma composition can change the level at which the volatiles start to emerge into a gas. So once volatiles exsolve, they nucleate, which just means they start to grow bubbles. And so here I've shown a phase diagram for water plus melt, and you can think of this as just being one of these binary phase diagrams where here we have the concentration of dissolved water. So on the left edge, this would be pure melt, in this case either basalt or rhyolite. And right down on the other side, we can't see it because we cut off at 6%, that would be pure gas, right? So you can think of this just like we did with the binary phase diagrams. Instead of temperature, we got pressure. And pressure ends up being probably the most important control on when and how volatiles exsolve. And so if we take what we call a water undersaturated melt, and this means that the melt has less water than it could hold. And here it's at a pressure of 1.5 kilobar. That's somewhere in the upper crust. Think about 5 kilometers depth. And if we just decompress it, so all we're doing is we're moving the magma upwards through the crust, and the pressure is dropping. Eventually, even without the water content changing, it hits volatile saturation. So what happens now, again, we can think of it just the same as our binary phase diagrams, is that the melt composition evolves down this line. So this field is just basalt. This field is basalt plus water. And it evolves down this line, and as the water concentration drops in the melt, we make more and more gas. So these are the radial vesicles. Now the amount of water I put here, 2% would be a lot for mid-ocean ridge basalt, but I've just done that because if I put it down at 0.5, then we can't really see what's going on. So, okay. Volatile rich phases, the behavior depends really, really strongly on pressure and temperature. So we're all familiar with liquids and gas, and this is just a pressure temperature phase diagram for water. And some of this should be super intuitive. When it's cold, about 0, we've got ice, solid. When it's warmer than that, we've got liquid. and when it's even warmer, we get a gas. Or if we drop the pressure a lot, we can also get a gas. But what happens at high temperatures and pressures is we reach this thing called a critical point. And at the critical point, it's kind of like the division between liquid and gas just goes away. And so on this side of the critical point, more towards gas, you'll have more kind of gas-like behavior. And on this side, you'll have kind of more liquid behavior, but it's a continuum. There's no discrete difference. So what's happening there is liquids as we know them, they're not compressible, right? They flow, but you can't squash them. Gases flow and we can squash them, and they're very low density. And with these supercritical fluids, they are higher density, more like a liquid, but they're also compressible, so more like a gas. So we're somewhere in between. However, if we go to low pressure and temperatures, then they're just going to behave as liquids and gases that we're all familiar with. So this is why we often talk about fluids when we're talking about stuff in the mantle. Is they're not really liquids, they're not really gases. These are these supercritical fluids, and sometimes there can be kind of a continuum between a supercritical volatile rich fluid and a volatile rich silicate melt. There's not such a hard boundary between them at certain compositions. All right, so volatile elements are elements that typically form volcanic gases, and the most important ones are water, carbon dioxide, and sulfur dioxide. In general, these behave as incompatible elements, just like the other incompatible elements we dealt with, but they can exsolve bubbles if they reach saturation. And at high pressure and temperatures, they're generally supercritical fluids, and they behave as gases at low pressures and temperatures. Does anyone have any questions about that? All right, so I'm just going to talk about the variation in volatile contents between some different tectonic settings, but first we'll start a bit with how we actually measure these, because it's a bit more complicated than just measuring normal major minor trace elements in a rock. And the problem here is that volcanoes degas upon eruption. So if we just take a rock and we measure the concentrations of volatile elements in the rock itself, they're always going to be lower than what was in the original magma. So it's quite hard to get at these original volatile contents. So one thing that people have tried in the past is basically to try and find samples that haven't degassed as much. One way you can do this is if you look for lavas that erupted under high pressure, say a mid-ocean ridge. They're covered in a couple of kilometers of water, right? So this means that because the pressure hasn't dropped, more of the volatiles will still be inside the lava and not exsolved as gas phases. A good example of this are these mid-Atlantic ridge popping rocks, which I've got a picture of in the top right corner. All of these round things are vesicles, so obviously they've exsolved a bit of gas, but they're called popping rocks because when people dredge them and bring them to the surface, they actually can explode on the ship's deck because they're still holding a bunch of gas in these vesicles. So in the past, people have done some very clever stuff looking at the vesicle size distributions to try and estimate how much gas was lost and get an original estimate of the volatile content. Another option is to directly measure volcanic gases as they're emitted. This is actually a satellite image measuring sulfur dioxide from a volcanic plume, and you can see it's erupted somewhere up here in Alaska. And then it's being spread out and dispersed by the wind. But essentially, if you could measure all of the gases that came out of a volcano and you know how much magma was there originally and contributed to that gas being emitted, then you could figure out what the original volatile content was. Another thing coming back to these mid-ocean ridge basalts erupting at high pressure is people try and look for volatile undersaturated compositions. So when you measure the composition in the magma, it has lower volatiles than the saturation amount at that pressure. So what you can then do is try and use these rocks to identify some sort of constant trace element ratio in a magma. And the examples I've given here are water over cerium. In these kind of undergassed rocks, they tend to show a pretty constant ratio. And so the idea there is that water is about as incompatible as cerium. So if you go somewhere else, you can measure the cerium and estimate the water. Obviously, this breaks down if you start looking at arc lavas because we know there's water being added and not cerium, or not as much cerium. Carbon dioxide over niobium, again, the implication is that carbon dioxide is similarly incompatible as niobium. So yeah, if you do this with mid-ocean ridge basalts, you get H2O over cerium ratio of about 100 to 250. So it's still fairly variable, but this is a way of guessing. But I think the way that most people seem to be doing this now is measuring volatiles directly that are trapped in melt inclusions. So the idea here is you go find a early crystallizing mineral like olivine, and you can see some really good pictures of them here. And some of them will have these little inclusions of melt, which appear as these dark circles in the mineral grains. This is, a section cut through it. And then you can actually measure if these olivines crystallize at a deeper pressure, a deeper depth, higher pressure than where the lava erupted, then you have a better shot of getting the original volatile content before any degassing happened. So, as we said before, volatiles are incompatible during mantle melting, and all of the major mineral phases, olivine, pyroxene, aluminium-bearing phases, that would be garnet or plagioclase or spinel, they're all what we call nominally anhydrous, and that means that they can take in a little bit of water as a trace element, but they don't have water in the formula. So it's not like an amphibole or biotite where there's an OH group in the mineral formula. So typical depleted mantle, and what I mean here is the mantle that's melting to give us mid-ocean ridge basalts, has pretty low volatile concentrations. So about 150 parts per million of water, 70 parts per million carbon dioxide, and 150 parts per million sulfur. It is fairly variable, but we're still talking these parts per million levels. And what's happened to these volatiles? Well, we said before that the depleted mantle is depleted because the continental crust has been extracted from it. And so volatiles lost from the depleted mantle are mainly in the atmosphere, the continental crust. And another thing I didn't mention here is obviously in oceanic crust that's reacting with seawater and being subducted and all this kind of thing. So, and I should also say oceans, of course, full of water. Okay. We can reintroduce volatiles into the mantle, though, by a process called recycling. And this comes back to the deep volatile cycling that I mentioned before. So the most obvious example of this is subduction zone fluids that go on to produce our fluid flux melting that come from the slab. These originate from seawater alteration. So the volatiles near the surface that are being brought down into the deep mantle. Most of those end up being driven off the slab at shallow depths, producing our fluid flux melting, and they end up being erupted through arc volcanoes or stuck somewhere in the crust. But some volatiles can actually survive to very great depths in the subducting slab, and they form these high pressure hydrous minerals. There's a whole bunch of possible ones that I'm not going to go into. But the interesting thing here is we know that these are going quite deep because we see earthquakes at great depth. And essentially because the pressure is so high, once you get to pressure of about 670 kilometers, which is where you see some of these earthquakes, that the only way you can have a fault, an earthquake, a kind of brittle rupture, is if you have some water or fluid down there that can sort of like remove, cancel out the effect of that pressure. Otherwise, the pressure from above is just too high for it to actually break. So we see these earthquakes in something called Wadati-Benioff zones. There's a upper zone, which is 100 to 300 kilometers, and then there's a lower zone, which is mainly, around 600 kilometers or so, and then it cuts off abruptly once we get to the top of the lower mantle. So some water is making it at least to the top of the lower mantle. I don't know personally if it gets any further than that. Go ahead, Oscar.
Earthquakes only happen on production zones?
Yeah. So we need something to get the water down there. And the thing with subduction zones, it's this combination of obviously stuff's moving down, but it's also cold. So we're not, it doesn't just melt, it doesn't get driven off as easily. Whereas I guess if you had some sort of convective downwelling, it would still be downwelling at the same temperature as the rest of the mantle, so we'd lose the water quite quickly. So aside from this kind of overall fluid fluxing, we can also get this local phenomenon called mantle metasomatism. And metasomatism just means it's almost like metamorphism, but you're adding something to change the composition. It's not staying at a fixed composition. And it gets typically used when talking about mantle rocks, although some people will talk about metasomatism when they're talking about crustal metamorphism. So what drives a lot of this is just the fact that wet and particularly carbonated peridotite melts at a much lower temperature than dry peridotite. And so if we are reintroducing carbon and water through subduction zones, yeah? Oh, just had carbon dioxide added to it. It makes carbonates. So when water and carbon dioxide get introduced into the mantle, they can make these very, very low degree melts, so tiny amounts of melting where we're melting carbonated peridotite, and it will make like a little squiz of magma that moves upwards, and it might freeze or react with the rocks around it. And what that leaves is these little veins of hydrous minerals or maybe more carbonated peridotite. I've given an example here. This is called the Marid suite because it's mica, amphibole, rutile, ilmenite, and diopside. But in this picture, you can see phlogopite. This is mica. Diopside. This is clinopyroxene. And this weird thing is called a K-eryctorite. It's basically an amphibole with a very unusual composition. And these are found in small veins in the continental lithospheric mantle. So we've had this continuous little percolation upwards of these tiny, small degree melts made from carbonated peridotite. So the main point I'm trying to make here is that broadly the mantle is pretty dry, but we have these local wet regions either due to subduction zones or these metasomatic melts that are moving around at very small melt fractions. Okay. So if we look at the water contents in magmas from different tectonic settings, mid-ocean ridge basalt, it's coming from depleted mantle, so we don't get much water, 0.3 to 0.5 weight percent H2O. And you can actually sort of, thought experiment this out. Well, we said that depleted mantle had 150 parts per million water, which is 0.015%, I think. Is that right? Something like that. So if we melt it by 10%, then we'd expect to get 0.15 weight percent H2O, right, from our melting equation. Now, it's a funny feature of the triangular melting region of Morb that you actually, it actually ends up slightly changing that melting equation. So we'd expect 0.3 weight percent from 10% melting of depleted mantle with 150 parts per million water. So sounds about right. In ocean island basalts, tends to be a little bit higher, and there's a couple of reasons for this. Because of the thick lithosphere, say in places like Hawaii, we might get slightly lower degrees of melting. Again, water's behaving as an incompatible element, so if we reduce the melt fraction, we actually end up with more in the melts. There's also potential that at these ocean islands, because we have a mantle plume coming from the deep mantle, we might be recycling some volatiles from ancient subducted slabs. And there's also some primordial volatiles. These are volatiles that were added to the mantle when the Earth formed, and they've never been released yet. So we can see that in certain things like the composition of noble gases, but I won't go into that too much. For primitive arc basalts, they apparently have quite a constant water concentration of about 4 weight percent, and this average of 4 weight percent seems to be the case in many different arcs with different subduction rates and age of oceanic crust and all sorts of things. So something's going on there, but this one's easy to explain. We've got fluid flux melting, we've got constant water supply, and even though the degree of melting is quite high in an arc, we are always adding water, and it's the water that's driving the melting. Yeah.
Is there more water in more involved arc settings or less?
Yeah, until you hit volatile saturation, then the water is going to keep going up as it becomes more evolved. So you would expect, say, an andesite to have more water than a basaltic andesite.
Yeah, but you said primitive arc.
Oh yeah, this is just this is basically what's coming out of the mantle. Yeah. And so the reason for focusing on the primitive ones is because then we can basically ignore all the fractional crystallization changes. I think in some dacites and rhyolites it can even get up to like 10-12%. It can be really quite a lot. So yeah.
Is there any difference in the volatile content between backite basins and rocks?
Yeah, and that's a really good question. There's actually a little bit more water in back arc basins. So even though we're mainly melting through adiabatic decompression melting, because there's not as much fluid being driven off, right? We're further from where the slab's going down. There is still some water coming off the slab, and that means that back arcs tend to be a bit wetter. Yeah. And I guess the next point kind of relates back to Bastian's question there. In all settings, as the magma gets more evolved, the water concentration keeps going up until we hit saturation. And this is simply because the mineral assemblage crystallizing is drier than the melt, so it's just behaving as a incompatible element. And that's true even when you start to crystallize amphibole and biotite, because amphibole will maybe have 2% water, biotite might have, say, 4%. But there are other minerals crystallizing at the same time, so the bulk partition coefficient for water in the crystallizing assemblage is still less than 1, so it still keeps going up. A brief mention of carbon dioxide and sulfur. So CO2 is a lot less soluble than water, and what that means is that it begins to exsolve at much higher pressures. And there's a plot here of water and carbon dioxide solubility and silicate melt pressure, and you can basically these lines are the saturation amounts of some combination of water and carbon dioxide, and you can see it 200 megapascals, so that's not actually quite sure how deep that is, but somewhere in the crust we can have up to 6% water, but we can only have up to 1500 ppm CO2, and if we go half that pressure we lose half our CO2. We've only lost a third of our water. And so what this means is that the concentrations of carbon dioxide in magmas pretty much always reflects degassing. It's very hard to get primary CO2 concentrations, but there's some estimates here. This is kind of what people expect it would have been before it degassed. So mid-ocean ridge basalts can be up to a couple of thousand ppm CO2. Arc basalts may be up to 1 weight percent in the primary melts, but I believe this is quite difficult to estimate. Because of all the kind of complex plumbing system and all that we're talking about, there's lots of opportunities for CO2 to degas. And in ocean island basalts or plumes, it's really variable. So you can have up to several weight percent CO2 in these kind of low degree melts. You might get an alkali basalt or something like that. But if you have a high degree melt, like a flood basalt where we've got a ton of melting, and it's going to end up being quite dry and low carbon dioxide concentrations. Sulfur, we're not going to go into, not because it's not important, but just because it's more complicated. The reason it's more complicated is it's dependent on how oxidized the magma is. So we said before that arcs are more oxidized. And in an arc setting, then sulfur is actually stable as a kind of anhydrite, which is sulfate ion, SO4 2-, in the magma. But in a more reduced setting, it's stable as a sulfide, so this would be, it would be like a dissolved form of pyrite. So both the amount of sulfur you need to reach saturation and what ends up forming, whether you whether you produce an iron sulfide liquid, which would be like a sulfide melt, or whether you produce some sort of sulfate gas, changes. So. All right, the main points there is that you can't measure volatiles just directly from lava compositions due to degassing. Need to use other methods, and I think the most common one now is looking at melted inclusions. Typical depleted mantle is dry, but we can reintroduce volatiles either by recycling at subduction zones, or they can move around in the mantle through these low degree melts and fluids, causing metasomatism. Mid-ocean ridge basalts are typically volatile poor, arc basalts are typically volatile rich, and plume magmas are variable depending on the degree of melting and the volatile content of the sources. Does anyone have any questions about that?
What does a melt inclusion consist of? It should be a sample of the original melts.
Yeah.
Why
So,
isn't the fractioned into gases and crystals and
so it can do actually, and so again, this is slightly beyond my area of expertise, but I think what people end up doing is, if it's fully enclosed, you can actually heat it back up to the point so you can sometimes see melt some crystals, even little gas bubbles in them, and you basically heat it and pressurize it until the gas bubble disappears. Then you quench it really fast, and then you can measure it directly. So
pretty fast?
yeah. So the gas is still dissolved in the magma. Yeah. Okay, talk about where volatiles end up and how they affect volcanic eruptions. So the most obvious thing is that they get released to the atmosphere during eruptions. Explosive eruptions, as I've shown on the left here, you release them as this big mix of gas and ash and chunks of rock in an eruption column. On the right here, you can see a basaltic flow, and it's basically just releasing gas as it flows along. So as it's cooling and crystallizing, gas is exsolving, bubbles are moving up to the surface, and they're just passively escaping. You can also get this kind of low temperature degassing we were talking about before. So one option are volcanic plumes, and it's almost like a volcanic eruption, but just a plume of volcanic gas. There's no magma, there's no lava involved. It's just these are almost pure gas. And the other thing are fumaroles, which are these vents through which volcanic gases continuously flow. This one up here is from Mývatn, which is a lake in northern Iceland, and I can't quite remember the name of the volcano it's associated with, but this place kind of looks like a moonscape of just, the soil's all kind of white and yellow and red and bizarre, and there's constant plumes of gas escaping, and there's some weird mud pots that are bubbling because they've got volcanic gas continuously going through them. So these gases are coming from fluids, right? They're in some sort of liquid or supercritical fluid form that's circulating around. They're being released perhaps from a magma chamber, and they're interacting with the rock around the magma chamber. And as they move, they can actually react with these magmas and the surrounding rocks to remobilize metal, forming ore deposits. And this is similar to the process we were talking about with black smokers in a mid-ocean ridge. You basically have like hot fluids moving around, they're dissolving metals somewhere and they're dropping them somewhere else. And this causes hydrothermal alteration. And this is a photo from this year, from the Spain trip, where we went to Rodalquilar gold mine. And I think you can see here, there's again these crazy like white and yellow and rusty red colors. And the rock's completely altered to shit. And over here, this is an active fumarole in Greece. So this is basically a hole in the ground that's spewing sulfur and other volcanic gases. And you can tell it's fairly deadly because I don't think it's in this picture, but there's actually a little dead bird in there, so it'd flown in and been asphyxiated. But anyway, often around these fumaroles, you get these kind of moonscapey, bizarre-looking rocks. And it's the same kind of process. Is we've got these hydrothermal fluids that are altering the rock, and once they get close to the surface, they're becoming gases and escaping. So I looked it up in the gold mine at Rodalquilar. It's something called an epithermal gold deposit, and this means that it's actually really quite low temperature mobilization of gold, maybe like 150 degrees C. So it was related to the magma chamber in that caldera there, and the fluid mobilizing the gold at quite low temperatures and dropping it off and creating this gold mine. And probably the thing you're most familiar with from looking at a bunch of lavas and seeing all the vesicles is these gases form bubbles. And this is hugely important for volcanology and the way that magmas erupt. So you're all familiar with pumice, which is pimpsten, my favorite Danish rock name. And this is basically almost purely made up of bubbles, right? And And once the lava is frozen, we call them vesicles rather than bubbles. On the right, it's the same figure I used in one of the mid-ocean ridge lectures of a pillow basalt, and it's got the radial vesicles of gas trying to escape out to the margins of the pillow. Okay. So this plot's a little busy, so I'll just talk you through it. But basically in the upper left to kind of middle, it's just showing the density of various minerals. And goes from oxides, which can be about 5 grams per centimeter cubed. Most of the ferromagnesium ones are a bit more than 3. So these, olivine, orthoperoxine, clinoperoxine. Peridotite is obviously a mix of these plus some aluminous phase, so it's about the same density. Hornblende, which is an amphibole. Micas or biotite is a bit less dense. And then down here we have all our kind of granitic minerals, alkali feldspar, plagioclase, quartz. And on the right here, we've got various magmas with the density plotted as a function of temperature. So the density changes when they heat up or cool down. And you can see that most of them here are kind of similar to this granitic rocks area. You know, the tholite melt about 2.6 grams per centimeter cubed, depending on temperature. And upper continental crust is pretty broadly granitic. So if we had something like a tholeiitic melt ascending through the crust, it could hit a level of neutral buoyancy and just stop, because it's the same density as the rocks around it. There's nothing driving it going upwards anymore. So the more evolved the magma gets as we get to andesites and rhyolites, they do get less dense because we're removing these dense minerals that crystallize early. We're removing olivine, we're removing pyroxene, we're removing amphibole. We're also obviously removing plagioclase, but the net effect is to make them less dense. But in comparison, gases formed by volatile exsolution are incredibly low density. So the density decreases really rapidly with falling pressure. This is a plot of, I think this is water. So we can see as pressure or as depth at 2 different temperatures, 1,000 degrees C and 7 degrees C. And here it's shown as a specific volume, so this is just the inverse of the density, and it's what people use for gases. But you can see here that especially as we get to like very low pressures, as we get very close to the surface, these are incredibly low density. They expand to massive volumes. And so magmas which have bubbles in them are much, much less dense than magmas that don't have them. So this can be a major driving force of magma moving up through the crust and eventually lava eruptions. Okay, so most volatiles in magmas are released to the atmosphere during eruptions in volcanic plumes or from fumaroles. Volatile rich fluids can also circulate through magma chambers and host rocks, mobilizing metals, forming ore deposits. And most importantly for us, for volcanology, volatiles exolving from magma form bubbles. These drastically reduce the density and they can drive magma movement and volcanic eruptions. Everyone still with me? Okay, I can't remember if that's the end of the lecture. There we go, easy. Okay, I'll just leave that up for a bit and we can take 10 minutes and then start back at 2:05.